beautiful people, and welcome. In this video, we are talking about infinite geometric series. Now, this is going to be a part 2 only for examples. Part 1 was recorded with the examples. However, the YouTube or the program that I'm using to edit my videos decided to cut me off midway or even in the beginning of example number 1. So I'm going to try to make this only for examples. I'm going to try to make this as short as possible, so I don't take up too much of your time. All right, so infinite geometric series, you have, watched part 1, so you know what that looks like. You need to have your formulas. I have written out some steps. Now, there's only one step. You need to, one step, I get my little bunny ears there. You need to determine first if the series converges or diverges. We know if it converges is if the R value, the common ratio, is less than 1, the absolute value of the common ratio is less than 1. We know the system diverges if the absolute value of the common ratio is equal to or greater than 1. So if R is less than 1, if the absolute value of R is less than 1, then we use the formula, and here it is. If greater than or equal to 1, if common ratio, the absolute value of the common ratio greater or equal to 1, then the sum does not exist, and we are doing a little happy dance because there's just less math for us to do. All right, let's start with example number 1. So the example number 1 says that we have 0.8 to the nth power, right? It's the summation of from 0 to infinity of 0.8 to the nth power. So that means my lower limit is 0. The upper limit does not exist because infinity is just a concept. You can always have infinity plus 1 and have one more of whatever that number you can imagine. So let's go ahead and also talk about this equation that they give us. They gave us an explicit formula. This is the explicit rule. Now, we know this is a geometric explicit rule because we have an exponent with a variable in it. That means it is an explicit rule. Now, I encourage you always to have a cheat sheet in front of you of all of the formulas. And the reason being is we want to confirm of what that, formula, this explicit rule matches, so we can find out what our A sub 1 and our common ratio is. So if we look at our cheat sheet, you're going to notice that we have a rule. I'm going to do a little thinking bubble here that says A sub n is equal to A sub 1 times R to the n power for when n, right, starts at 0. So when n starts at 0, so we can also say like greater than 0. So that means the lower limit of this equation is 0. We have a lower limit of 0. That also means that the number in front of here, so I have my R, I have my N, so that means this is my R, obviously this is my N. Then the number in front of my R value is my A sub 1. Because nothing is there, that means my A sub 1 value is 1. Because anything times 1 is anything, right? So if we multiply 1 by 0.8 to the nth power, we just get 0.8 to the nth power. That helps us out because we have our formula to find the sum of the infinite series. Now, before we continue, we need to determine if the series converges or diverges. That's always your first step. So step number 1, we want to see if it converges or diverges. So our R value is 0.8, and the absolute value of 0.8 is in fact less than 1. So we know that it converges. We are happy about that, and we're going to use the formula. The formula is right here, the summation of n equals 0 to infinity is A sub 1 divided by 1 minus R. So let's go ahead, just down below, rewrite that formula just a little bit bigger, but this time we know what our A sub 1 is. A sub 1 is 1. And we know we have 1 minus R. 1 minus R. R is 0.8. Calculator time. Whenever you do this, like this one here, I like to use the calculator to do the denominator first. And then, let's see if I can do this. And then I have the rest. Ooh, wrong one. So I have 1 minus 0.8. That is 0.2. So I'm going to have 1 divided by 0.2. 1 divided by 0.2 is 5. So as our position numbers get infinitely large, position number 375, position number 376, etc., we're going to get exponentially closer to 5. And that's pretty much it. Let's go ahead and do one more example. Example number 2, same process. First thing I'm going to do is I'm going to check for converging or diverging. My absolute value of r, here's my r. Again, r is always attached to the exponent. It doesn't matter if the exponent is n or n minus 1. That just tells you the position number it's starting at. In this case, we have an n. Look at your formula sheet. That means the position number is 0. That's the formula they gave you. So that means this is r. So I have the absolute value of 1/5 is smaller than 1. So that means it converges. I'm not going to write the formula again. I do have it. You can't see it, but I do have it here ready for me to use. One thing I do want to point out is the formula. I will actually scroll back up. Here's the formula. This is matching. How do I know? Because this is n and this is n. So that means this is r. This is r. So that means just like before, this is going to be our a sub 1 or our first term. So because this is a sub 1, this here in our formula, this a sub 1 technically is an a sub naught or a sub 0. Because we start at position number 0, this a sub 1 is technically our a sub naught, but that's our first term in the first position. So going back down here, because we have our formula, this is the a sub naught or a sub 0. So if we have a list of numbers, here it is, and it goes off to infinity, the first number that we see in the 0th position is -5. The common ratio that we have is that we are multiplying by 1/5 each time. Okay. So that means with the, super important, you guys, with the lower limit of 1, so this is our lower limit. Let me change my color. That means that the a sub naught, or the number in the 0th position, is excluded. It is not in our summation. Because the lower limit, it basically cuts you off here. The lower limit is at a sub 1, or the number in the first position. We need to find out what that number is in order to use our formula. I guess I will write the formula. So our summation is equal to a sub 1 divided by 1 minus r. Again, this a sub 1 here, that just means your lower limit, the number in your lower limit. Doesn't actually mean a sub 1. It's the number in the first number that you take. So if this is 3, this would be an a sub 3 on the top. Alrighty, let's go ahead and figure some stuff out. We want to find out the term in the first position. You can do this different ways. You can use the formula, or you can just use the common ratio. So if I have -5, I multiply by 1/5. That means the term in the first position for my lower limit is going to be -1. So when I'm using the equation, I'm saying -1 divided by 1 minus r, and this is 1/5. Once again, I like to do the denominator first. That's just me. So I do 1 minus 1 divided by 5. So that is 4/5. And then I do -1 divided by my 4/5. And that is -5/4. So this series gets exponentially close to negative 5/4. It gets super duper duper close to negative 5/4. The larger my position numbers are, the more numbers I have, the closer I get to negative 5/4. All right, beautiful people, I'm going to go ahead and wrap up this video here. Please make sure you know the difference of the lower limit given the formula in relation to the formula. Also know that lower limit of 1, if you're given the formula for position starting at 0, make sure that you are aware of that. Hopefully this video does not get cut off. As always, thank you for watching, and I will see you in my next video. Bye.